Okay, so for the last lecture, we're going to talk about the role of surfaces in nanocrystal growth, sort of a departure from what we discussed last time, which was really mostly about homogeneous nucleation and classical ideas about crystal growth thermodynamics. Before we do that, though, I just wanted to remind you of one or two ideas. So last time we talked about how precursors, these thio and selenourea compounds, their reaction kinetics, how fast they break down into solutes, can control the number of particles. And this is something that was anticipated by Sugimoto and formalized by him in his mass balance equation. And that's been thoroughly demonstrated now on a variety of different metal chalcogenides. There are also examples in other material systems. And we talked about different growth models. So we set up this kinetics of diffusion picture where you have monomer diffusion to a sphere and you get this depletion region that has a width. And the width of that region is related to how fast the surface reactions happen. If the surface reactions where the monomers reach the particle and stick instantly, if that process is really fast, then you can get these depletion regions and you can get diffusion limited growth kinetics. And we compared two limiting situations, one where the surface reactions are really slow, and under those conditions you get the kinetics of growth that are only determined by attachment, and then you have little or no diffusion sphere around the particle. The concentration at the particle surface is the concentration in the bulk solution. But in other cases where attachment is fast, then you can end up with a large diffusion sphere, particularly if the diffusivity is low and diffusion is slow. And that gives rise to diffusion controlled growth. And you get two different linear growth rates here. This is the linear growth rate for the diffusion controlled case that's related to the diffusivity and also related to the particle size. Whereas over here, the linear growth rate is not controlled by particle size to a first approximation. And so, that means that under diffusion controlled conditions, small crystals grow faster, and you can get a phenomenon called size distribution focusing. Normally I would talk more about this, but we just ran out of time. But I will say that, the only existing, or I would say the only established mechanism for size distribution focusing relies on this diffusion limited growth mechanism. And, it's actually, just because the topic is kind of fun and there's a lot of papers about this, I'll say that diffusion limited growth and size distribution focusing are phenomena that depend upon the supersaturation. Okay, so normally remember we talked about Oswald ripening. When you have small and large particles together in a mixture, the small ones are more soluble. They break into pieces. The big ones are less soluble. And this is something the Gibbs-Thompson relationship has laid out for you. And so the small ones fall apart while the big ones grow. And this gives rise to Oswald ripening, right? Freezer burn on your ice cream being a good example. But this only really is a meaningful process where the small ones dissolve and the big ones grow if the supersaturation is low, or, if it's at equilibrium or quasi-steady state. If the supersaturation is high, then all particles grow, right? You don't dissolve under conditions where the supersaturation is high. So all the particles grow, and under those conditions, the growth rate of the small ones can be larger if it's under diffusion limited, in a diffusion limited growth mechanism. And that gives rise to size distribution focusing, according to Howard Rice. And there are papers about this and how the growth rate of different sizes, changes with time. And anyway, I'm not going to get into it. Um, but this mechanism of size distribution focusing by diffusion limited kinetics is actually something that most people say is important, and I do not think that it has been shown in just about any example in the literature. Now, there's a lot of examples out there, so I'm sure I'm missing some, but um, this is one explanation for why nanoparticles have narrow size distributions, but in most examples, it's not really been clearly shown. Okay, so I'm going to put that stuff down and transition away from that a little bit. But this slide is helpful for the next couple of slides. So um, over here on the left, I've plotted this heat of formation or energy of formation as a function of the size of the crystal. And, Gibbs-Thompson relationship says that the bigger they are, the more stable they are. So it goes down. But here at small crystal sizes, you get these minima. And, we're talking about less than 100 atoms or something like that. The difference between adding or subtracting an atom here or there is not constant. It's like it is at much larger sizes. At much larger sizes, you add or subtract atoms, and the average energy difference is very small compared to the whole, and so you get a smooth relationship. But at really small sizes, where you have a few atoms and a molecular kind of a size, you get these dips. And these dips people refer to as magic-sized crystals or clusters. And there are a lot of them. And I would say I've shown some classics here. Ian Dance and Dieter Fensky. I mean, these guys, really, Fensky has published, I don't know, thousands of different metal chalcogenide clusters of different metals, copper and silver. Apparently, if you go through his labs, you'll see, poster upon poster upon poster of cluster molecules that have been crystallized and never published. Anyways, there are a lot of them. And the reason they form is really all about ligands. Okay, the ligands dictate a particular size. So I've shown you some examples here in the upper right where you can see the ligand sphere. It's the binding of those ligands that sort of stops them from growing and leads to a molecular type of a structure. In the chemistry of metals, you can get closed electronic shells that are important, but in semiconductors like these, really it's just the surface energies that are leading to these particular sizes and formulas. This same kind of phenomenon also appears in nanoplatelets. So these are a few monolayers thick, say 2, 3, 4, 5 monolayer thick crystals of cadmium telluride here in this image, but lots of different materials make these colloidal nanoplatelet type structures. And they have large lateral dimensions. This is probably 100 nanometers and 50 nanometers, something like that. And so, in the thinness direction, you have a molecularly uniform structure. In the lateral dimensions, it's like a regular old material. You have, it's not molecular in the same way, although notice there are very nice straight edges here. But the difference between 100 nanometer width and 110 nanometer width is not going to be great. So the reason these platelets form, as I mentioned in the past, is really about the binding of ligands and the binding of carboxylates with a small R group to the 1,0,0 facet. Acetate makes these types of crystals stable because it packs well. And so, minimizing the surface energy or really taking advantage of the strong metal ligand bonding gets you into these type of structures. Okay, so crystals favor particular shapes and sizes and formulas that are dictated by ligands that bind very strongly. And that gives you these kinds of molecularly uniform type of structures. So let's take one close example, take a close look at an example of one made by Oswald ripening. Okay, so this is going to be a case where Oswald ripening actually leads to a molecularly defined product. And I'm just going to take one quick step back here and say, you're used to looking at the absorption spectrum of nanocrystals of cadmium selenide changing smoothly as you go from small to large. You add a few atoms, the spectrum shifts to the right. Um, but there are examples, quite a few examples in the literature on cadmium selenide and other metal chalcogenides where you don't see a smooth evolution of the spectrum. And you'll find the spectrum jumps from one peak maximum to the next, particularly at very small sizes and high energy. So these are a series of aliquots taken over time during a synthesis. And if you look at this peak here, you'll see that it increases in intensity and then decreases in intensity. And as it's decreasing in intensity, a new peak is appearing, and then a new peak appears. And so really these are just jumping from one peak size to the next. And this has been dubbed quantized growth by my former postdoc, Brandy Cosaire. And Brandy developed conditions for studying the same kinds of reactions under in a slightly different way. And so I'm showing you some of those results here. What Brandy did was to make cadmium benzoate with two amine ligands and then react it with bis-trimethylsilyl selenide. Um, and that makes cadmium selenide. And actually, because this silicon selenium bond is quite labile, it's not a very strong bond. And the silicon oxygen bond is a strong bond, and the cadmium selenium bond is a strong bond. This reaction is very far downhill and happens at low temperature. So um, Alex Beecher, another student from my group, studied this reaction at low temperature. So he found that these two compounds react with each other at minus 40 degrees. And you can see the spectrum of the starting materials in red turn into a new spectrum that in blue out here in the ultraviolet region of the spectrum. You pile up this absorber at minus 40 degrees, which is frozen acetonitrile temperature. And then if you take that same flask and you warm it up to ice bath temperature, you'll see this absorption go away and a new absorption appear. And if you take it out of the ice bath and you let it warm up to room temperature, you'll find this tooth spectrum disappear and a new one appear. And that process continues. If you heat the synthesis, it'll go to the next largest size. And if you heat it hotter, it'll go to the next largest size. And so you can watch it jump from size to size. Now, the precursor reaction here, the TMS selenide reaction with cadmium benzoate, is finished at minus 40 degrees after an hour. So, all of the cadmium selenide in these data here is formed at minus 40 after an hour. And so what you're watching in this case here is an Ostwald ripening process where these clusters, or whatever this is dissolving, and this new cluster is precipitating. And again, at minus 20, or at room temperature, this cluster dissolves, and this one precipitates or grows. So all you've done is converted 10 millimoles, or whatever the scale is on which he ran the reaction, from one cluster size to the next without adding any new material. So it's just rearranging and heading downhill. The other thing about this data, which we're not going to talk about, but is a good thing to be aware of, are these very interesting crossing points. Notice how all of the spectra that are in here, there's many different spectra going from this time to that time, and they all cross at these points. These are called isospestic points. And when you see them, it's an indication that you have two things interconverting. And at these points, the two objects have the exact same extinction coefficient. And so the sum will always be equal to that absorbance. when the two things have the same extinction coefficient. So um, that tells you that there are no intermediates piling up. It's really just one cluster turning into the next cluster. And interestingly, this data allowed us to prepare this one example cluster very carefully and isolate it and get an X-ray structure of it. And it's really just a simple pyramid of the zinc blende structure. There's a lot of work behind all this. And so I'm just going to jump ahead and say that we did that for a couple of different pyramids, all of which are shown here. And so you remember I said if you heat it, you can actually cause one pyramid to turn into the next, and really it's to the next largest pyramid. And if you take that pyramid and you heat it, it turns into the next largest pyramid, all by this cannibalistic Ostwald ripening process. And one of the interesting things about this reaction, I mean, there are a number of them. Of course, the molecular uniformity of the products is a very important aspect. But then also look at the chemical formulas for each of these pyramids here. You're going from 20 cadmium selenides to 35 cadmium selenides to 56 cadmium selenides. Those are not integer multiples of each other. And so it's pretty hard to imagine how you take that little guy and get to the next largest one unless you invoke molecular fragments that are small. Okay, and so these things are breaking up into units as they grow. They also have the expected metal-rich formula here of the surface chemistry that we've talked about, metal enrichment, and really these pyramids have pure cadmium termination. So all their facets are terminated with cadmium, and they have this number of ligands that bind, and these ligands here, this guess of the formula, this number of ligands corresponds to the number of dangling bonds. Okay, so each of these pyramids achieves a fully saturated type of a structure. So each of these pyramids achieves a structure where all of the surface ligand bonds are where all possible, or I guess where a complete coordination sphere for each of the cadmiums has been achieved. And that is the origin, as I've been proposing, of their particularly stable size. And you might be thinking, well, I thought you said, Professor Owen, that you can't do that because the surface atom densities are higher than the ligands can pack. On a normal 1-1-1 facet, the atom density is higher than the alkane chain areal density of perfectly crystalline chains. But these little objects are curved, and that makes additional space for the organic ligands. Okay, and it's one of the reasons I think that these particular structures are stable. They are small enough where the volume available to ligands around those pyramids is about 2 to 3 times higher than a flat surface. So the ligand packing here helps to stabilize these particular clusters. And that is possible because of the small size and the high curvature. Okay, so one more very interesting tidbit about this that is quite relevant. Back to this idea that the building block that's being exchanged here to do this Ostwald ripening must be very small. And so you might imagine a mechanism where you have a pyramid. Let's see, where did you go? Where's my pointer? There we are. So take your pyramid here, and we're going to grow it. So you break it apart into these soluble units. And those soluble units then have to deposit onto another pyramid to grow it to the next size. And so in the middle of this reaction that we're running here, where this one's going away and this one's appearing, in the middle, you have an equal amount of both the small cluster that's dissolving and the big cluster that's forming. And so those units now have a choice as to whether they're going to deposit on the smaller pyramid or the larger pyramid. And because of the fact that this is so selective for this next size, as long as you keep the temperature low, it must be true that these units preferentially adsorb to these small clusters over the large ones. They don't seem to react with the large ones. If they did, then you would get the next largest size, which is starting to form here. But for the most part, really, you only go this way. The soluble units do not add to the larger pyramid in this mixture. Okay, and so this is telling you that this Ostwald ripening process that is dictated by the energy of forming a surface is selective for the small pyramid. It dissolves the small pyramid preferentially, and the monomers attach to the small pyramid preferentially. And so a natural consequence of this is that small crystallites are more reactive toward growth than large crystallites are. And so that is I think this is a very suggestive finding that, in fact, growth dynamics of surfaces are size dependent, and that even under conditions where you have attachment limited growth kinetics, where the thermodynamics of that surface and the barriers to attachment are the dictating force in the growth kinetics, you can still have a size-dependent growth rate. And in other words, you can get size distribution focusing this way, which is what you're seeing here. You are watching a size distribution focusing process that's happening during an Ostwald ripening reaction, because the small crystallites are more reactive toward growth than the larger ones. Okay, so you know that some of those findings gives rise to some kind of energy diagram that's like this, where the energy of formation is going down, so it's becoming more thermodynamically favorable to grow to the next largest size. But it also says that there's some barrier to attachment that is increasing as you get to the next largest sizes. So, you know, when you're here and you're deciding to go forward, you know, and maybe you have a mixture of these two, the monomers don't go over this hump, they only go over this hump. Okay, so anyway, a very interesting example of how the kinetics of the reaction are dictated by the surfaces, and yet you still have size-dependent growth. All right, so I want to transition now and start talking about metal nanocrystals, which is another case where there's an awful lot of evidence to suggest that surface reactivity is very important to the growth mechanism. So here we're going to talk about the conversion of metal salts, say palladium chloride or silver bromide, and their reaction with some kind of reductant. Okay, so we'll look at it. Hydrogen, alcohols, citrate, and that reductant converts the metal salt into some metal cluster nucleus. Okay, so it's a reduction of the metal salt to make a metallic cluster, and the production of some Rx byproduct. If this were hydrogen, this would be hydrochloric acid, or you know, some hydrogen carboxylate or something. Okay, in metal chemistry, this turns out to be kind of hard to do, because these little tiny metal clusters are very unstable. So metal atoms, or few atoms of metal zero, tend to be very unstable toward aggregation. And you know, it's difficult to make metal zero starting materials for that reason. And so generally speaking, metals are very insoluble. Okay, and so this gives rise to some barrier for producing these little metal nuclei. But once you form those metal nuclei, they react with metal salts by adsorption. And then those metal salts on the metallic particle surface react with reductants more quickly than the metal salt in solution does by itself. Okay, and this gives rise to something called autocatalysis, where the formation of metal leads to a more reactive precursor. And the conversion reaction then takes place on the metal particle surface, okay? So you form the cluster, and the cluster then catalyzes the conversion reaction, and suddenly it speeds up. And this has been demonstrated by a number of people. And I'll just say briefly, one more mechanism that tends to be very important in the growth of metals is growth by agglomeration or coalescence, where two metal particles get together and kind of sinter and form a new metal particle. There's a lot of examples of this kind of thing in metal particle literature. So I'm going to talk about that step in any depth, but I'll show you one example of this autocatalytic formation mechanism that was something put forward by, I don't know if he was first, but has been studied in depth by Rick Finke at Colorado State. And he's developed a number of different model systems. One of them is shown here, where you take this cyclooctadiene platinum dichloride complex and let it react with hydrogen in acetone solution in the presence of bases, and you make a platinum zero nanoparticle product that has a negative charge and some outer sphere countercation, like the one shown here. At the same time, in the presence of hydrogen, you convert the cyclooctadiene to cyclooctane. So you hydrogenate olefins with the hydrogen, and the platinum zero particles that form turn out to be quite good at that reaction. They pick up hydrogen, you make platinum hydrides on the surface, for example, and those convert the cyclooctadiene into cyclooctane. So, this is an example of an ion pair adsorption to the surface of platinum zero. There may be some platinum 2 in here as well to help kind of make the ligand stick. It's not clear, not important for the discussion right now. And Finke, in order to study these reactions, he started looking at the hydrogenation process. Okay, so he started making platinum zero and then using the platinum zero colloids to catalyze the conversion of cyclohexene to cyclohexane. This is a typo. This should be cyclohexane. So he's hydrogenating cyclohexene to cyclohexane. And what Finke says is, hey, this hydrogenation process gets faster with time as I deposit platinum zero. And so I can use this cyclohexane formation reaction or the hydrogen consumption process to monitor the production of metal. As I produce more catalyst, my system becomes more active and I consume more hydrogen. So I can use the hydrogen consumption kinetics and the cyclohexene to cyclohexane hydrogenation process to extract the formation of metal. Now, here's an example of what one of those data sets looks like, where you've got cyclohexene at some 1.5 molar concentration at time zero. You add the hydrogen, and what you find is that nothing happens at first, or very little happens at first. And you got to wait a couple of hours, but then all of a sudden, boom, hydrogen consumption turns on and the cyclohexene concentration starts to drop. And so, this pause, this delay or induction period here for the first couple of hours, and this very rapid consumption process, this is a sign of autocatalysis. Something gets made in those first couple of hours, and as you make it, the reaction system sort of turns on. And so this is Finke's evidence for autocatalytic growth, and he spends a lot of time fitting those curves to extract the rates of nucleation and growth and aggregation under these conditions, and things get very complicated very fast. But this is the main evidence for a surface catalyzed reduction of the metal salt in the formation of platinum zero, iridium zero, and others. And, you know, it's sort of become recognized more widely that this is an important process in transition metal chemistry. Okay. Um, so I think this is clear, but making this initial cluster is difficult. The product metal is very insoluble, and the metal salts are more stable. But then once you have the metal zero in solution, the absorption of metal salt and the reduction of metal salt gets faster. And so, you know, you make some clusters and all of a sudden the conversion turns on and hydrogen consumption turns on very dramatically. Um, Another kind of reaction, a very important class actually of particle forming reactions are the kinetics of forming or the synthesis of gold and silver. Uh, a very classic example of this kind of thing is the reduction of gold chloride with citrate. And what you get in the end are gold nanoparticles with citrate ligands bound that lead to an electrostatically stabilized colloid. Okay, so this gold particle is some mixture of gold zero and gold plus, to which citrate adsorbs, and then the other carboxylates of the citrate molecule balance charge with some outer sphere sodium ions, and this will give you very stable colloids in water solution. Okay, the reduction here gives rise to this byproduct. So you make carbon dioxide, um, and you extract the electrons from the CC bond to do the reduction process. So it eliminates CO2, and you end up with this ketone in place. Um, and you know, it's thought that this reaction, or there's evidence to suggest that these kinds of reactions are also possibly autocatalytic. Um, there's better evidence in other types of cases where, for example, instead of citrate, you can use hydroxylamine as a reductant. And you know, as long as you keep out um, sites for heterogeneous nucleation to take place, it turns out that hydroxyl ammonium chloride is not a very good reductant at 100 degrees in water. And so you can actually heat the salts with that stuff and you won't make particles. But if you add seeds to those reactions, now this reduction process can happen. And so when the reductant is selective in this way, when it's not powerful enough to make gold zero on its own, you'll get preferential reduction of the gold nanoparticle and autocatalytic growth. So there's not, I haven't seen an example where somebody's shown an induction delay in the formation of gold and interpreted it to mean autocatalysis, but this is a clear signature of that kind of thing. Another type of gold nanoparticle synthesis that, you know, of the few kinds of reactions that really are important is what's called the Brust synthesis, named after Matthias Brust. And what he did was to take gold chloride, gold 3 chloride, and cooked it up with some ammonium halide salts and produce these ammonium haloorate ion pairs. This stuff is soluble in organic solution if the R groups on the ammonium are aliphatic. And so you can take this organic soluble gold salt and reduce it with sodium borohydride in the presence of a thiol and produce gold nanoparticles that way that have thiol ligands, or I should say thiolate ligands bonded to the surface. Okay. So this is a very well-known reaction, pretty successful reaction. There's a number of variants on it, but it's been shown that the size control under these conditions can be controlled by tuning the reactivity of the reductant. So more reactive reductants give rise to greater number of particles in a smaller final size. And you can actually adjust that by just converting some of the borohydride into these carboxylate borohydride salts. So as you knock off hydrides, you end up with less and less reactive reducing agents and slower kinetics, and then larger particle sizes. So clearly precursor limited nucleation in this case, unlike some of the other ones. And that's reasonable because you have a much more reactive hydride source, and the homogeneous conversion of gold salts to gold zero is much faster under those conditions. So it also turns out that in the synthesis of gold, one of the main ways that size is controlled is not by controlling the extent of the nucleation and all of that, but using what's called digestive ripening. So digestive ripening is a underappreciated type of reactivity, except by people who synthesize gold, although it is kind of gaining in popularity or in people's minds um, recently. And it's unusual because digestive ripening will take large nanoparticles with a broad size distribution and convert them to smaller ones with a narrow distribution. So this interconversion actually looks like it's uphill to me. If you just have Gibbs-Thompson theory in mind, and you have typical Ostwald ripening type of a scheme in mind, this is going the wrong way. You shouldn't take a broad distribution of large things and make a narrow distribution of small things. Okay? And so this is kind of disobeying one of the sort of classical tenets of particle thermodynamics. Um, uh, and you know, this is a reversible type of a process too. Another interesting thing is that you can take this and heat it with a different type of a surfactant, different surface ligand, and all of a sudden get back this broad distribution and large size and go around the horn here. So I would say that this is maybe not a widely accepted, or it's more of a proposal than a certainty, that this formation of a narrow size distribution with smaller size must be a sign that the surface energy here is favorable. In other words, it's not normally in the classical picture, surfaces are unfavorable. You have a surface tension. But in our case here, the formation of surface is a favorable quantity, and the system takes a low surface area starting material and makes a high surface area product in order to take advantage of the gold thiol bond. So there is a driving force for making surface area because the surface ligand bond is favorable. And so the system is trying to maximize surface area um, uh, that is dictated by a certain ratio of ligands to metal. And if you knock those ligands off using a different surfactant, that can go away. Okay, so there's something special about gold and thiols, which should be familiar to everybody, I would imagine. And in this example, that plays out by leading to this narrow distribution. That's a thermodynamic product, okay? And that is unusual and interesting. So let's transition now to talk about transition metals. Boom, boom. Let me see what time it is, just to make sure. Okay. All right. And so transition metals and coinage metals have been made into nanoparticles many, many times over using colloidal methods, and you often obtain these wonderful cubes and octahedra and cube octahedra of different sizes, often with wonderful monodispersity. And you know, there's a variety of different strategies for making metals of this kind, but one of the most widely practiced is the alcohol-based reduction of a metal salt. And so I've shown an example where ethylene glycol is used to reduce silver nitrate to make silver metal, and producing this butane dione byproduct. Now, this kind of reaction is a very well-precedented reaction in transition metal chemistry, the oxidation of the CH bonds next to an alcohol or next to an amine. And so primary alcohols and primary amines and diols like this are frequently in the mix when trying to convert a metal salt to a metal zero. Um, and, this is another case where you have an alcohol, which is a relatively mild reducing agent. I mean, one doesn't typically think about an alcohol as being a reductant, but if you pair it with an oxidizing metal salt like silver nitrate, suddenly it does become a reductant. And so it will reduce things like nickel and palladium and platinum and iridium and rhodium, um, and metals that want to be in their metal zero state. But an alcohol like this is much less likely to make chromium metal, for example, which is itself a good reductant. So alcohols are nice and selective reducing agents. It's a very sort of mild way to convert metal salts into metal zero. And so under conditions like that, you're not very likely to nucleate metal by itself, and it really helps to have some sort of a surface on which to nucleate it. And people will sometimes add sulfide to these mixtures to make a little bit of silver sulfide. And then that silver sulfide can undergo reaction with the diol and the metal salt in some fashion to form metal zero. So you can see these reactions and get around the homogeneous reduction step and just do the surface catalyzed one. Now, people often add other stuff to the mix. One of those things, surfactants, for example, to stabilize the product dispersions. And so one of them that's very popular for metals is this molecule, PVP here, polyvinyl pyrrolidinone. So this is a very polar polymer. You add it to the mix with the silver nitrate and the alcohol, you cook it up, and you get these wonderful cubes at the end. A cube shape like this for these sorts of close packed systems, the cube facets are the 100 facets, and the corners are 111, and so on. And I know we haven't done much discussion of crystallographic facets, so you don't need to worry about that too much. Just remember, for a cube, you have an XYZ origin sort of coordinate system, and those X, Y, and Z coordinates you can line up to point at the faces. So the 100 refers to the X direction, the 010 refers to the Y direction, the 001 refers to the Z direction, and it's just a way to name the faces, okay? So PVP added to the mix gives you cubes. It's also the case that adding halides to these syntheses, or beginning with metal halide salts, frequently leads to cubes. And you can also run these same kinds of reactions, but instead of adding PVP or halide salts, you add citrate again. And now the conversion gives you a different shape. So here, instead of cubes, we're now making these little decapod type structures. These are pentagonal bipyramids. There's a real nice example down here. And they have facets that that are favored by the citrate molecule. Okay, it turns out that this is a multiply twinned structure, and these surfaces are the 111 surface of an octahedron, but you actually have 5 different little octahedral pieces sandwiched together to give you this pentagonal type of a structure. In any case, you change the ligand in the pot from PVP to citrate, and you suddenly have a different nanoparticle shape. And so what is going on there? Another thing I should mention is that these little decapods actually turn out to be good seeds for making other types of things. And so metal salt reduction produces nanoparticles often that then go on to very interesting shapes in the end. So for example, take this multiply twinned decapod here, which is 5 pieces of the metal. And if you grow those decapods on, they have a tendency to, well, sometimes they'll form icosahedra, but they also can lead to a pentagonal rod shape. And this has to do with the twinning that's denoted by these red lines here. and you end up with these twin planes along the length of that rod. If you get a different type of a seed that has a different twinning structure or twin structure, like the singly twinned object here, you can get a right bipyramid or a beam, or if you get a doubly twinned type of a seed, it can go on to form platelet-shaped metal crystals, hexagonal or triangular platelets. And so one mechanism of shape control here in this material system is to form a seed that has a predisposition to make a particular shape, often dictated by some kind of internal defect or twin arrangement where two crystals are stuck to each other, and that leads to this anisotropic growth. But that's not the only mechanism of shape control. So I talked to you about the citrate and the PVP giving these different shapes. Yeah, here's an example of the decapod turning into a rod. But in addition to the seed type of the thing, it turns out the cube and the octahedron, they have the same internal structure. Okay, so those particular shapes come from crystals that have no twins. But the growing crystal adopts a shape that relates to ligand binding. Okay, so this diagram up here shows you how a cube and an octahedron are related by a cube octahedron. So if you preferentially add silver ion to the 100 faces, and you don't grow these gold faces, which are the 111 faces, as you grow, you'll start filling out in that direction along 111, and you won't fill out along you'll grow along this direction here, but you won't grow where the yellow stuff is, and that 111 facet will then increase in area with time. Okay, and so citrate ligands tend to lead to these octahedra because of the fact that the citrate probably binds to those surfaces and slows down the conversion of the metal salt on those facets, and it allows the 100 to grow. And vice versa, if you don't have citrate but you have PVP or bromide, you can have the other type of situation. So here, the ligand dictates the shape that you get by favoring a particular surface structure. And people have shown that this happens in cases where you actually start with seeds of one material that can be, I think this is platinum inside of palladium. You have a little cube of platinum, you add it to a crystal growing synthesis and use it as a seed crystal. And then you can dictate whether you want to grow a cube on top of it or a cube octahedron on top of it or an octahedron, depending upon what the other surface ligands are. Okay, so the shape is really dictated by how surface ligands favor or disfavor certain facets over others. So a very important principle in this context is what's called Wolff's theorem. Wolff's theorem says that a particle will achieve a shape that attempts to reduce its total interfacial free energy. Okay, so the different shapes have different energies, and those different energies are really dictated by surface ligands, how they bind and what abundance they're found. Also, the energies of facets that don't have ligands bound to them. And so the particle will assume a shape, or there'll be a driving force to take on a shape that minimizes that surface energy. And so people for a long time have said, okay, well, you can estimate the energy of a facet by just calculating how many bonds are broken on that facet. Okay, so if you take a face-centered cubic structure, the surface tension or the surface energy of that facet is basically the number of bonds broken per unit area times the bond association energy. And so if you compare the 100 and the 111 facet, the two that are important for making octahedra and cubes, there is what is that, 0.6. So you're talking about, you know, a 20% difference in energy between those two facets, that is all dictated by the number and density of dangling bonds on those two surfaces. Okay, and so you know that you can calculate what the proportion of the area would be. You know, you're going to have 80% more 100 than you are 111 for a metal particle in the gas phase, just by counting the number of dangling bonds, and that works pretty well. Of course, in a real system, you don't just have dangling bonds. You have reconstructed surfaces that rearrange and take on a different shape, or you have ligands that bind, and the ligand binding can dictate how thermodynamically favorable that surface is. So lots of examples of how surface energies dictate uh, um, particular sizes and shapes. Another very important one is illustrated here, and this is the formation of magic-sized metal particles. So this is, if you take metal and vaporize it, and you look at the types of fragments you find in the vapor, what you'll find are different, what are called magic number clusters of metal, um, where the clusters take on a particular shape and a particular size that minimizes the number of dangling bonds. So you see these closed facets, complete facets and corners and whatnot, perfectly uniform geometrical shapes formed in the gas phase, where the next largest one is just the addition of one more shell of atoms. Um, and that's consistent with this sort of Wolff's theorem picture. All right, so I'm sorry, I don't have a conclusion slide here on this material, but you can see that in this class of reactions and in general, not just metals, also in the chemistry of semiconductors, the energies of forming the surfaces are very important to the growth mechanism, not only in controlling shape, but also in controlling the relative reactivity of small and large crystals. And that's very important to the size distribution. So although people teach this classical picture about the free energy going down, the bigger the particle gets, and the surface is just being a source of tension, and you know the objective is that surface tension dictates the nucleation, it actually turns out that ligand binding strength is really important to the types of materials that can be made and the mechanisms of their formation. And the surface ligands and their energies are probably also very important to size distributions in a way that has not been spelled out. And so, you know, the community of people in this space is kind of grappling with this. My group is grappling with, I am grappling with these ideas, and trying to come up with a uniform way to talk about them, and to take advantage of them to make higher quality materials. Okay, so I'm going to stop here, and maybe I will fill out a conclusion slide before posting the notes.